Okay, we will continue talking about the stuff we had just launched into on Thursday. Relations and functions. Remember what we said about that? We said relations really are just ways of relating inputs to outputs. And we're going to look at some examples of those today. What was unique about functions? Functions were special relations. What caused a relation to graduate to the level of a function? What was our rule? You fill in the blank. For each input, there's exactly one output. Exactly, right. So we said, for example, that the green relation, just a set of, how many points are in that set? Show me with your fingers. Yeah, 4 points, right? 4 points. I've got 1, 2, 3, 4 separate ordered pairs, so 4 points. Same with this, with the red relation, but the green one was a function, and the red one was not, because in the case of the red relation, the input 1 appeared twice with different outputs, and so it failed the rule to be a function, because there was an input, x equals 1, for which there was more than one output. So that one was not a function. And we left off just talking about the vertical line test. Right, the vertical line test is just a quick way, if we can see the graph of a function, it's a quick way of determining, or graph of a relation, it's a quick way of determining whether that relation is a function. If we can sweep a vertical line across the graph, and the vertical line could never intersect the function in more than one place, then it passes the vertical line test, and it's a function. So the green graph passed the vertical line test. That was a function, but the red one was not. So give me thumbs up and thumbs. Oh, and then I want to leave off with this. We never quite got to this though. So we got to keep all this stuff straight, right? We've got ordered pairs, usually our variables are x and y. We've got inputs and outputs into these relations. And then we said that the set of all inputs was called the domain, and the set of all outputs was called the range. Well, it's really easy to keep track of which goes with which, because all of these occur in alphabetical order. All of the first, the parts of these two pairs of different items that go together, the one that alphabetically comes first, they all go together, right? X goes with input, which goes with domain. Those three all are alike. Alphabetically, the one that comes last, in each of those cases, those also group together. The outputs are typically Y's, and the set of all outputs is the range. Okay, so you tell me, thumbs up or down, does this relation pass the vertical line test? If I sweep a vertical line across this, am I good? Yeah, I am. Absolutely, it does. It never intersects the graph in more than one place. So yeah, that is a function. How about that one? Thumbs down, absolutely. And we can see why, obviously, here. There's an example right there. The function is intersected by the vertical line in more than one place, so that is not a function. These were both examples of continuous relations, because they're ones I could graph by keeping my pen on the board the whole time. Do you remember what we called one like that, where I have to pick my pen up multiple times? Starts with a D. You know what we called that? Call that a discrete relation, one where there's a whole bunch of places where I have to pick my pen off the board. And in this case, what would each of these, so this graph of this relation, each one of those points corresponds to what? What would that look like if I wanted to represent this relation not as a graph, but maybe as a set of something? What would all those somethings be? What do you think? You see anything up here that if I graphed it might look like that graph? What do you think? just a bunch of dots on a screen. What were those dots? They're points. Okay, how do we represent points in math? What do we need to represent a point? Like, for example, can you tell me something about this point right there? What can you tell me about that one? Say it again. Okay, 10, 8. So you said an ordered pair. Yeah, we could represent that point with the ordered pair 10, 8. So if I wanted to represent all of those points, what would that relation look like? I mean, how would I represent those? What would you expect to see? Say it again. So XY, a bunch of XY coordinates. Okay, so we could write that as a set of points, right? I could write that as, for example, I could use set brackets and I could start off, there's 1, 10, 8, and I would have a bunch of others, right? And I'd want to kind of, well, I mean, really any order would be fine, right? That's one way to do it. We'll talk about some other ways today also. Is this relation a function? Thumbs up or down? Be careful here. Oh, I'm seeing some thumbs down. Where does it have a problem? Let's see. It looks like so far so good. I'm passing the vertical line test, but let's see. It looks like eventually I run into a problem right there. Those two line up vertically. So this relation, so it fails the vertical line test, doesn't it? So is this a function? No, it's not. Okay, give me thumbs so far. How are we doing? Thumbs up, down, sideways. We good with all this stuff? Is this ringing a bell? Remember talking about this stuff, vertical line tests? And it's been a while, but I'm sure you talked about this stuff. Okay, so now let's practice working with it a little bit. So here's a bunch of different representations of relations. So first we've got a couple that look like sets of ordered pairs. So sets of points. So first of all, give me thumbs up or down. Is this a function? Got to vote. I got to know where we are on this. What do you think? Is that a function? Seeing lots of thumbs up. Yeah, it is. It is. What's the domain? And by the way, be careful with this, because when we write the set of the domain, we always want to try to write the elements in ascending order, so numerical order. So what would my domain be here? Okay, so -1, 0, 4, 6. So the x coordinates were already in order, weren't they? Okay, what's the range? There you go, -9, -5, -2, and then 3. Okay, good. And you said it was a function. And why was it a function again? Each input only has one output, right? Okay. How could you quickly, like if you had to do a whole bunch of problems like that, how could you get really efficient and fast at it? What did you look for there that gave you a clue immediately that you didn't have to worry? This was a function. Say that again. Oh, look for repeated x values. And there were none, right? There were none. Okay, how about number 2? What's the domain here? -3, 5, and 8. The 5 shows up twice here, doesn't it? Do we have to list that twice in the domain? No, we don't. Exactly. Okay, so. And the range? -6, 0, 2, 4. Okay, give me thumbs on this. Is this one a function? Okay, good. Lots of thumbs down. How come? Yeah, 2 5s, right? So we get the input 5 is paired with the output 2 and the output -6. If you just looked at nothing more than just the sets, what if we didn't even see the points, but someone just gave you the domain and the range of this relation? Is there a way that you could infer that this is not a function? How? Yeah, there's only 3 inputs and 4 outputs, so that means at least one of those inputs has to occur twice, right? So this one is not a function. All right, good. Okay, here's another way that you're already familiar with. Another way to represent relations is with a t-table, right? So we've got an x column and a y column. We talked about these a little bit the other day. Remember that we like these because then when we look across a row, they look like ordered pairs, okay? So tell me here, number 4, is this, give me thumbs on this, is this relation a function? I agree, looks good. Looks good. What's the domain? 10, 15, 18, 24. All the x coordinates. And the range? 0, 3, 7, 11. Good. Okay. All right, so now something different. This is what we call a mapping. Give me a 1 to 5 on, have you ever seen these before? What's your familiarity with a mapping? 5 meaning really familiar, 1 meaning not at all familiar. I'm kind of just curious. Okay, I'm seeing lots of low numbers on this. So a mapping, no big deal. All a mapping does is it's going to group, you know, we got this, the domain is grouped inside one blob. The range is grouped inside another blob. And so we can see all the elements of the domain are just going to appear as elements inside that first domain blob, right? It's just a set, but it's contained inside. Usually it's going to be like an ellipse. Inside the range, we've got all the elements of the range. And then the arrows, what do the arrows do? Say it again. Okay, so it's telling us which input is paired with which output, right? So that's actually defining the relation. An input of -4 maps to an output of 0, for example. So if I wanted to write that as an ordered pair, what would this arrow look like as an ordered pair? Yeah, that one would just look like -4 in, 0 out, right? Give me thumbs on that. Does that make sense? So the arrows are important here. Okay, so what's the domain of this relation then in number 5? -4, -2, 5. Good. Okay, give me thumbs. Everybody agree with that? Okay, what's the range? 0, 3, 7, 9. Okay, thumbs up or down. Is it a function? Absolutely not. And what's the dead giveaway on this one? Okay, there are 2 arrows leaving the input 5. So that's an absolute giveaway. That 5 is an input that pairs with 2 separate outputs. And so this one is clearly not a function. Okay, what about number 6? What's the domain on numbers? Actually, we won't even bother with the domain and the range. Just tell me thumbs up or down. Is 6 a function? Is that relation a function? Yeah, I'm seeing lots of thumbs up, but how come I see 2 arrows pointing at 7? Is that a problem? How come that's not a problem? You're right. Because why? Okay, because the inputs are all different, right? Each input only pairs with one output. The input 2 has an output of 7. The input 17 has an output of 7. So it passed the rule for functions. Each input only has one output. Does it matter that 2 of the outputs happen to be the same? No, that's fine. That's fine. That's really okay. What's not okay, if this is going to be a function though, is something like this, where one input has multiple outputs. So even though these arrows both point at the same number, this is still a function. Okay, give me 1 to 5 on that. How we doing? Does that make sense? Okay. What would that amount to? Well, we'll look at an example here in a second. I think we will. Okay, what would that, I guess maybe I took that page off. So what does that look like? Like if I were going to graph all of those ordered pairs, what about those 2? Let's look at those 2 ordered pairs. 2, 7, and 17, 7. How do those line up if I were going to graph them? they have the same y values but different x values. So how would those things, yeah, okay, I'm seeing a lot of people doing this. They would line up horizontally, wouldn't they, in the xy plane. So that's okay. That's okay. There is no horizontal line test that we have to pass. There's only a vertical line test. And those points would not overlap vertically. So we would still pass the vertical line test there, wouldn't we? Right, so we'd be fine. Okay, and then finally, what about 7? What's the domain of this relation in question 7? What is it again? -3, 0, 2. How'd you get that so fast? And then 4. Maybe that last one was covered up. What's the trick there? How'd you get that one so fast? What do you do there, somebody? How are you going to get the domain? You're going to read that off so quickly. Okay, you're looking at just the x coordinates as you scan from left to right. Everybody agree? That's all you're doing. Looking at the x coordinates of the points you encounter moving from left to right. Okay, what's the range? -5. -2, -1, 1, and 4. Okay, good. And what'd you do there? How'd you get those so quick? Yeah, just going bottom to top. You're just moving in the positive y direction, from the bottom to the top, looking at all the y coordinates. Is it a function? No, it's not. How come? Those two, right? They fail the vertical line test, don't they? They line up vertically, so nope, it's not. Okay, what about one like this now? This is a little bit different. So this is kind of where we got to practice this stuff a little bit. So this is a different kind of relation than we've seen in all the previous examples. This is one that's continuous. So how many points were included in this relation? Show me with your fingers. 5? Okay. How many points were included in... How many points were included in this relation? 5 or 4? Okay, good, good. How many were included? You get the idea. How many were included in this relation? 4. Yeah, there were 4, weren't there? How many are included in that relation? Infinite. Yeah, right? Because it's continuous. So really what this is this is in math we'd say it's a locus of an infinite number of points, just a collection or a set of an infinite number of points that are all jammed together to create that one continuous object, right? That one continuous curve. You can think of it like a piece of wire with an infinite number of beads on it that just blur together and make one line. So what is the domain of that relation? All real numbers. How'd you get that? How did we get all real numbers? That's the set of all the x coordinates, right, or the inputs. Explain that. It has infinite, right? Okay, good. And we weren't able to say, like, even if the domain were something like x, all the values from x equals 2 to x equals 4 or something, that still would be an infinite number, wouldn't it? Right? But how come this time we just say all real numbers? Okay, but there's something about this that kind of gives us a clue that we have to include all real numbers for our input. What is it? Because it doesn't look like, I don't see the number x equals -51 included there, but I can infer that it is. How come? The arrows. What do the arrows mean? It's just going forever following that path, right? So the fact that we have an arrow that points to the left forever means that all the values of x that continue to the left forever are included, same to the right. So it's the arrows that really give this one away, right? So the domain is all reals. What's the range? All reals, because it looks like this continues upward forever if an ant is walking to the right. And if an ant were walking to the left, he'd be walking down forever, right? So again, all reals. And give me thumbs on this. Is this a function? Yeah, how come? Okay, what does it pass? The vertical line test, yeah. Okay, good. All right, so let's look at another one of those. How about number 9? Okay, take a second and look at that one. This one's a little bit different. How many elements are in the domain and the range of this one? There's an infinite number of values in the domain and the range. But the domain's a little bit different this time. What is the domain? I can't just say all reals. Is the x coordinate 10 included in the domain? Give me thumbs. X equals 10. I see people shaking their heads. I'm seeing some people shaking their heads yes, and some people shaking their heads no. We got to figure this out. Is x equals 10 included in the domain of this relation? I won't call it a function yet. I agree it is. How come? Wesley, what's going on? How do you know that? Okay, because, well, these arrows, these are both straight. They're both straight, aren't they? I mean, because we have an arrow that indicates that it's going to do this pattern forever. So if an ant walked along this bottom part of the relation, wouldn't his x-coordinate eventually reach 10? I mean, we can't graph an infinitely large function, right? We always have to choose what's going to be the domain in the range we're going to look at. What's our viewing window? But I could zoom out if I wanted to, presumably, right? Because that arrow continues to the right, and that one continues to the right also, doesn't matter, no matter where the ant's walking on this top piece or the bottom piece, that ant is eventually going to get to x equals 10, or x equals 100, or x equals a trillion, right? So those are all elements of x that are values of x that are included in the domain. What about -5? Is -5 included in the domain? Thumbs up or down? Definitely not, right? The ant only goes to the left so far when he's walking on this relation. What's the leftmost point that an ant could ever get to? What x value? -4. Okay, so then what's our domain? X is what? Okay, so what's a way I could say that with an inequality? To -4. Okay, so there's one way to say it. Good, I could say x is greater than or equal to -4. Give me thumbs on that. Does that make sense? Okay, because that includes all of the infinite x values in our domain. How could I say that with interval notation? Okay, I could say it -4 infinity. What kind of enclosures would I have to include with this? Bracket and parentheses. Good, okay, good. Now, how can we get that? I mean, you can see it from the graph, but there's a way to think about this that's kind of important. It's not something we're going to do a lot with this year, but in math, eventually, this will play a huge role in math in the future. We could take what's called a projection of this relation. If we were to squish this entire thing onto the x-axis, or imagine that I'm going to cast a shadow on the x-axis by shining lights vertically from below and above. The shadow that this thing cast on the x-axis, wouldn't it start at -4 and just move to the right forever? Everybody see that? So that's the projection of this function onto the x-axis, and that represents the domain. Everybody see that? Okay. What's the range? Now that is all reals, isn't it, right? Because an ant could continuously walk from -infinity to +infinity by staying on this relation, right? There's no y values that would ever be skipped. So the range would be all real numbers. How would I say that using interval notation? Okay, good. Just negative infinity to positive infinity. And isn't that what the projection of this thing would look like? Now, where would I be shining the light this time if I wanted to project the function onto the y-axis? Yeah, from the sides, horizontally, right? And it would just cast a shadow, an infinite shadow along the y-axis. Everybody see that? Okay. Is it a function? No, clearly not. And what test does it fail? The vertical line test. And here's an example of where it fails. If I look at a vertical line right there, for example, look, there are multiple points that line up vertically, so it's not a function. Okay, what about this ellipse over here? How many points are contained in the ellipse? How many points are contained in that ellipse? Could I ever zoom in far enough to see discrete values? No, I can't, right? Mathematically, I can zoom in as far as I want to, and it's always just I'm always gonna see an infinite number of points in my viewing window. Even if I just focus on one little piece of this and zoom in, it's always gonna look continuous, isn't it? Right, so there are an infinite number of points building that ellipse. Okay, but they are contained within finite values, finite ranges of x and y. Our domain and range would both be finite here. What is the domain? Okay, so values from x equals -2 up to +5. So how would I say that using inequalities? So how do I write that? If I were going to write it from left to right, what would I write first? -2. Okay, that's how I write it. Now, how do I say it? Okay, we start in the middle, don't we? With a triple compound inequality, we start in the middle. X is greater than or equal to -2 and less than or equal to +5. Okay? What's the projection look like on the x-axis? Where does it start? If I want to graph the domain, I'm shining light vertically on this thing. Where would the shadow start? What x value? -2. Would the projection have a solid or open or closed endpoint there? Closed, because the point x equals -2 is a place where the ant could stand, right? So I'd have to have a closed endpoint there. Oh, what did that do? I don't know what that did. I don't think I could ever do that again if I tried. Okay, so then it just would travel over and it would end at +5 where I'd also have a closed endpoint. How would I write that using interval notation, the domain? With brackets, good. Okay, what's the range? So it goes from -2 up to 4. Would I have open or closed endpoints if I graph that projection? Closed, wouldn't I? Because the ant could stand on y values at -2 and +4. So it's pretty easy to see that as an interval. How would I write that with inequalities? Okay, let's go ahead and say it correctly, and I'll write it correctly. X is the x variable the y is -2 and less than or equal to 4. Good. Is it a function? Obviously not, right? It fails the vertical line test. Good. Okay. Give me 1 to 5 so far. Is this making sense? Okay, you're going to get a chance to practice all this. Okay, how would we do one like number 11 at this point? Because we haven't really talked about, I mean, we could make a t-table to sketch this thing. That's fine. We could do that. if you didn't have access to technology, but let's assume that we do, right? What am I probably going to do, practically speaking, to see a graph of that? Because that's what I need. I need to see a graph of this function at this point. Later on, after we've talked more about quadratics, you'll be able to tell me what the domain and the range are just by looking at that equation, right? Get those Chromebooks all the way close, please. But for now, we're not there yet. We need to look at a graph. What would I do to graph this thing? Where would I go? Desmos graphing? Good. Where's another place you could go? Your graphing calculator. They still don't have my emulator installed. When they do, we'll take some time and go back and kind of talk about the graphing calculators a little bit. But you guys probably know how to graph this stuff on a graphing calculator. Just go to Y1 and type that in. If we did that, it's going to show us a graph, and we'll be able to base our domain and range off of the graph. What about one like that? Let's skip up to these for today. And this, I think this will be, yeah, this will be where we'll leave off for today. What would that graph look like? Y equals -7, do you remember? Vertical line? Oh, I'm seeing horizontal lines. I think horizontal. How come? Okay, because what this is telling us, and we'll talk more about this when we review lines, we'll talk about this again. What are the math gods telling us here? They're telling us that, is there an x in that equation? So the math gods are saying x doesn't matter. But y is always equal to -7, right? So every point on this relation has to have a y coordinate of -7, right? X could be anything, but it's irrelevant, because if I know what the y coordinate has to be, I know what this thing looks like, right? It has to look like a horizontal line at -1, 2, 3, 4, 5, 6, 7. So it has to look like that, doesn't it? Okay, so what's the domain of this function? All reals, right? What's the range of this function? -7, that's it, right? X equals -7. How could I write that as y equals -7? How could I write that as an interval? I mean, really, it's just going to look like parentheses -7, parentheses 7, right? Okay, we could also write it this way. We could also write this as just the set -7. We've got discrete values, and we want to list those discrete values. We really don't need interval notation there, because there are no intervals. They're just discrete values. So this is where we'd go back, and we would just have a set of values, right? When we just have only specific values, and that's it, right? Okay. Is it a function? Give me thumbs. Yeah, it is. Passes the vertical line test. Okay, how about this one? What about the relation x equals -1? What are the math gods telling us? Y doesn't matter. Y is irrelevant, but all x coordinates have to be. Okay, so then this one looks like a vertical line. Right? What's our domain? X equals -1, which I could write as the set that includes only -1. What's our range? All reals. What if I wanted to write that using interval notation? Good. Is it a function? No, a vertical line miserably fails the vertical line test, doesn't it? Right? Okay, that should get you going. The first assignment is up there. If it's not, I'll put it up there.